Okay, we are going to start to discuss physical layer from the data communication and networking book, 4th edition. Okay, it's chapter number 3, data and signals. Okay, so as we have discussed that in the TCP IP protocol suite, there are 5 layers. There are 5 layers: application layer, transport layer, network layer, link layer, and physical layer. Till now, we have discussed application layer, transport layer, network layer, and link layer. And now we are going to discuss physical layer. Okay. So, when the message is generated from the source, from the users, so it is passed through application. The application, it passes the message to transport layer. The transport layer, it adds its header. Then the message is passed on to the network layer. The network layer, it also adds its own header, and then the message is passed to data link layer. And the data link layer, it's also add its own header. Then the message, the data link layer pass the message to physical. Okay, so what is the functionality of physical layer? The physical layer, it physically moves the data over the link in the form of signals. So the physical layer functionality is what? To move the data over this link from this end to this end, from this end to this end. Okay, so the physical layer functionality is to move the data over the link. Now the data in this system, it is in the data form, and the link, it supports signals. So the data okay, so the physical layer has 3 tasks. First is that the data is converted to signal. The physical layer, it has 3 tasks. First, it converts data to signal, because the on the medium, on the link, the data is propagated in the form of electromagnetic waves signal. So the data link layer, the physical layer, its functionality is to convert data into signal form. And when it is received at the receiving end, okay, so here the physical layer, it converts the signal back to data form. So the first task is to convert data to signal at the sending side, at the one end, at the sending side of the link, and at the receiving side of the link. At the receiving side of the link, the physical layer, it converts signal to data. And the third is controlling the physical layer, because there may be different channels. Okay, so this is the functionality of physical layer, to map the data to a particular channel. Okay, so we are now considering the physical layer. So when we finish the physical layer, so we will complete the 5 layers, the TCP/IP protocol suite. So the physical layer, it moves the data over the link in the form of signals. Okay, so it has 3 tasks. The data is converted to signal, and the signal is converted to data, and controlling the physical layer. Okay, so now we are discussing how the signal and data is represented. Okay, so we will discuss the signal, and then we will discuss how data is converted to signal. Okay, so first we are going to discuss the signal, and then we can discuss how the data can be converted to signal, and how signal can be converted to data. So we will discuss it later, but first we are going to discuss the signal, that what is signal and how it is represented. Okay, and what is its phenomena. Okay, so this chapter 3, it is totally about the signal. It is about signal. Okay, so we have already discussed it. Okay, the encapsulation, decapsulation, these are discussed. So to be transmitted, the data must be transformed to electromagnetic signals. Okay, so we have discussed that the first task of the physical layer is to convert the data into signal at the sending side of the link. Okay, so to be transmitted over the link, the data must be transformed to electromagnetic signals. Okay, there are basically two types of signals. One is called analog and one is called digital. Okay, both the data and the signal, data can be analog or digital. Okay, for example, the analog data refers to information that is continuous, for example voice, and the digital data, it refers to information that has discrete state, for example data stored in the computer is in the form of zeros and ones. So analog data, it takes continuous values, while the digital data, it takes discrete values. Okay, so the data, it can be analog and digital. Similarly, the signal can be analog and digital. Okay, so the data can be analog or digital. Analog data are continuous and take continuous values, and the digital data, it has discrete state and takes discrete values. Similarly, the signal can be analog or digital. Okay, the analog signal, it can have an infinite number of values in a range, while the digital signal, it can have only a limited number of values. So as the data can be analog and or digital, similarly the signal, it can be analog or digital. Okay, so the analog signals can have an infinite number of values in range, and the digital, it can have only a limited number of values. For example, this is the analog signal. For example, this is analog signal. It is continuous. And this is digital signal. It has a discrete values, either higher or low, higher or low, higher or low. So it has discrete values, but here the analog signal, it has continuous. Okay. So similarly, the continuous signal, it can be of two types. One is called periodic signal. Periodic signal, it completes a pattern within a measurable time frame. For example, from here to here, this is one pattern, one cycle. This one cycle is completed in this time, and this same time it completes another signal, another cycle. Okay, so this is called that it is analog, it is periodic, that it is repeating this pattern in the same time. This is called periodic signal. A periodic signal is one that completes a pattern within a measurable time. In equal interval time, it repeats the same pattern again and again. This is called a period or a repeat that repeats the pattern over subsequent identical periods. So, for example, in 1 second, it takes one cycle. It completes one cycle. So, in the next cycle, it also completes the same cycle. Okay, same cycle. So, this same pattern, it is repeated in each and every second. This is called periodic signal. If the same pattern is not repeated in the same second, in same time interval, then this is called non-periodic signal. For example, here you can see this is a here pattern, the next pattern is this one, the next is this one pattern. So the pattern is changing. This is called aperiodic signal. Okay. So basically in data communications, we commonly use periodic analog signal and non-periodic digital signals. So periodic analog signal can be classified as simple or composite. A simple periodic analog signal is a sine wave that cannot be decomposed into simpler signal, while a composite signal, it can be decomposed into multiple sine waves. Okay, so we will, for example, this is a simple sine wave. Okay, so this is simple sine wave. Okay, and we will discuss that. For example, we may have composite signal. For example, we may have a composite signal like this one. This is a composite signal. This is a composite signal. Okay. So we will discuss about it later on. Okay. So till now we have discussed that the data, it should be changed to signal when it is to be transmitted on the link. So the data can be two types, analog and digital. Similarly, the signal can be two types, analog and signal, and one is called periodic signals. So we are considering periodic analog signals. Okay. Now a signal, okay, are electromagnetic waves or a sine wave. It is basically represented by three parameters: amplitude, frequency and phase. Amplitude, frequency are time periods and phase. So a sine wave, it has three components: amplitude, frequency or time period, or phase. Okay. So let's discuss what is amplitude, what is frequency, and what is phase. So the amplitude, the peak amplitude of a signal is the absolute value of its highest intensity, and it is proportional to the energy it carries. It is proportional to the energy it carries. For example, you can see that in this signal, the highest amplitude is this. If this y-axis, it is representing amplitude, and the x-axis is representing the time. So this is the highest amplitude. This is the highest amplitude. So this is called the amplitude. This is called amplitude. This is called. So here the amplitude is, this is amplitude for this wave. This is the amplitude for waves. This is the amplitude. Okay. So the highest peak amplitude value, it is called the amplitude. Okay. So this basically shows the intensity of a signal. So you can see this signal has amplitude value, peak amplitude value lower than this signal. So this signal is of high intensity as compared to this signal. This signal is of high intensity as compared to this signal, because this signal, it has peak amplitude value higher than this one, and the amplitude value, it is basically measured in volts. It is measured in volts. So it is basically representing the energy that it carries. Okay. So you can see that in this signal they have, okay, so the amplitude, it represents the highest or the peak amplitude values. Okay. Now what is period? Period refers to the amount of time in second a signal needs to complete one cycle. So the period or time period, it is the amount of time that one cycle is completed. Okay. So let's discuss it. For example, you can see one cycle is completed in this time. So time from here to here, this is called time period. This is called time period. Okay. The time period means the time period, it is the time that a sine wave complete one cycle. Okay. So you can see that in this signal, it completes the one cycle from here to here. So this is the time, and here this signal, it completes one cycle in this time. So here this time is larger than this time. This time is larger than this time, and this time period, it can be also described from another perspective. You can see that in 1 second, how many cycles are completed. How many cycles are completed? So how many cycles are of a signal is there in 1 second? A signal completes how many cycles in 1 second? This is called frequency. This is called frequency. And so the time period, it is represented in second. It is measured in second, but the frequency, it is measured in hertz. It is measured in hertz. So frequency, so the period or the time period, it refers to the amount of time in second a signal needs to complete one cycle. So a signal completes one cycle and the time in a time, that time is called time period. And frequency refers to the number of cycles, the number of periods in 1 second, that how many cycles are completed in 1 second. This is called frequency. Okay, so the frequency and the time period, they are inverse of each others. They are inverse of each other. Frequency equal to 1 by time, and time is equal to 1 by frequency. Okay, so you can see that here this signal, it has time period like this one. So this time period is shorter as compared to this time. So here in 1 second, how many cycles are completed? 1, 2, 3, up to 12. So it means that its frequency is 12 hertz, because in 1 second this signal completes 12 cycles. But here in 1 second it completes 6 cycles. So it means that its frequency is 6 hertz. So the number of cycles in 1 second, it is called frequency. So here in 1 second it completes 6 cycles. So its frequency is 6 hertz. So the frequency is measured in hertz. Okay. So we have discussed two things, amplitude and frequency. So similarly, you can see that these are the time period. Okay, so this time period value can be converted to hertz. These are its equivalent hertz value. Okay, so suppose if the power we use at home house has a frequency of 6 hertz, then what is its time period? So time period is equal to 1 by frequency. So 1 by 60 hertz, this is the time period. Okay, so frequency can be also referred as the rate of change with respect to time. Rate of change with respect to time. You can see that basically it is how the signal change in unit time. How many times it change? How many times the signal change in a unit time? So this is can also be called frequency. Change in a short span of time means high frequency. Okay, it means that if the signal change in a very short span of time, it means high frequency. If the change is slower, then it is called lower frequency. For example, you can see that here the frequency is high because in 1 second it changed 12 times, but here it changed 6 times, so it takes 6 cycles. So here the frequency is lower as compared to this one. Here the frequency is higher. Here the time period is lower, and here the time period is larger. Okay, so if a signal doesn't change at all, then it means that its frequency is 0. And if a signal changes instantaneously, then its frequency is infinite. Okay, next we describe phase. Okay, so phase basically describe the position of the waveform relative to time 0, and it is measured in degree or radian. For example, you can see that this is the time period, time 0. So here the signal start. So the signal start with 0 degree. So here its degree is 0. Here with time 0 it start from here. When time is 0, the signal start here. So here the degree with respect to this line, the degree is how much? The degree is 90. It is 90 degree. And here the degree is at time 0 it start here. Okay, so the signal start from here. So the degree between this and time 0, it is about 180 degree. Okay, so basically this shows the degree, the phase. This is called phase. Phase is the degree of the signal wave with the time 0, Okay, so these are the 3 sine waves. Their frequency is same. Okay, their frequency is same. In the same time period, it covers the same number of cycles. In same time period, it covers the same number of cycles. So frequency is same. The amplitude is same. But the phase is different. Here the phase is 0, here the phase is 190, and here the phase is 180. Here the phase is 90. Okay, so this is, for example, an example. Okay, so you can see that the total degree is about 360, from 0 to 360. So total degree is 360. Okay, so if a sine wave is offset 160 cycle with respect to time 0, So 360 by 160 it is equal to 60 degree. So it means that its phase is 60 degree. Okay, and its radian is pi by 3. Okay, so now we have discussed three things of a sine wave: amplitude, frequency, and amplitude, frequency, and phase. Now another important component of a wave is called wavelength. It is called wavelength. So the wavelength is the distance a simple signal can travel in one period. So you can see that this is from here to here. This is one cycle. So in one cycle, how much distance is covered? So the distance covered from here to here, this is one cycle. So the distance covered in one cycle, this is called wavelength. Okay, so the wavelength, it depends on both frequency and medium. It depends on both frequency and medium. Okay, and the wavelength, it is equal to c by f. F is the frequency and c is the speed of signal waves. Since the electromagnetic waves, its speed is equal to speed of light, which is called c. So that's why lambda is equal to c by f. Okay, so now a signal, it can be represented in time domain. And time domain means that the signal x-axis is the time, that in time, with respect to time, how the signal varies. With respect to time, how the signal varies. And the y-axis is its amplitude. But in the frequency domain, the x-axis is representing the frequency. So it means that the signal is represented in term of frequency. Okay, so here you can see that its frequency is changing with respect to time. So therefore it is represented like this way. If this sine wave is represented with in time domain, then it will be represented like this way. But if it is represented in this frequency domain, so its frequency is how much? In 1 second it completes 6 hertz. So its frequency is 6 hertz. Okay, so in the frequency domain, it can be represented by just one line. It can be represented by just one line in frequency domain. Okay, so it is much easy. Okay, so a complete sine wave in the time domain can be represented by one single spike in the frequency domain, as I have explained it. Okay, this wave, it is representation in the time domain, and this wave, it is representation in the frequency domain. Okay, so the frequency domain is more compact and useful when we are dealing with more than one sine waves. Okay, for example, in figure number 3.8 shows 3 sine waves, each with different amplitude and frequency. For example, here you can see that we have 3 different frequencies. One is this sine wave, second is this is the blue one, this is the green one, and this is the pink one. So they are very complex, but if they are represented in frequency domain, then they will be represented like this way. Here the frequency is 0. Here, because there is no change, so its frequency is 0. So here it is. Here in 1 second, this is completing 8 cycles, so its frequency is 8. Its frequency is 8. And here it represents in 1 second 16 cycles, so its frequency is 16. So here these 3 signals, they are represented in frequency domain, so it is much easy to understand. Okay, so signals and communication. A single frequency sine wave is not useful in data communication. Okay, up to now we have discussed, this is called single frequency. Okay, so the simple or single frequency sine wave, it is not useful in data communication. We need to send a composite signal, a signal that is made of many simple sine waves. So according to Fourier's analysis, this is a sine test. Any composite signal is a combination of simple sine waves with different frequency, amplitude, and phases. So in data communication, we basically use composite signal and periodicity. Okay, so if the composite signal is periodic, then Decomposition gives series of signal with discrete frequencies. And if the composite signal is non-periodic, then the decomposition gives a combination of sine waves with continuous frequency. For example, we can see it. This is a composite periodic signal because it is repeating itself, its pattern continuously. Okay, so this is periodic. Okay, composite signal. So its decomposition could be like this one. So it is composed of three frequencies. You can see it. One is this one, another is this one. Okay, we are going to decompose it. For example, this signal is decomposed of three signals. One is this one is this one, and one is shorter one. Okay, for example, one is this one, and the other is, for example, another one. Okay, so you can see that this composite signal, it is decomposed into three signals. Okay, and these three signal, it is represented in time domain, but if it is represented in the frequency domain, then this will be represented like this way. Okay, so similarly here, this is the time and frequency domain of non-periodic signal. These are non-periodic signals. Okay, so what is the bandwidth and signal frequency? Okay, so the bandwidth, it is basically of a composite signal is the difference between the highest and lowest frequency. The bandwidth is what? It is the difference between the highest and the lowest frequencies contained in that signal. For example, this is a signal, a composite signal. It has the signal with the frequency from 1000 to 5000. So 1000 is the lowest. For example, here the frequency is starting from 1000 to 5000. 5000 is the maximum frequency. So this is 1000 is the lowest. So 5000 minus 1000, it gives 4000 hertz. So this is the bandwidth. This is the bandwidth. So the bandwidth of periodic signal, it is the difference between highest and the lowest frequencies in a composite signal. Okay, so for example, if we have a periodic signal, a composite signal which is composed of sine waves with the frequency 100, 300, 500, 700, and 900. So here the lowest frequency is 100 and the highest is 900. So 900 minus 100, it gives 800 hertz. So it means that its bandwidth is 800 hertz. 800 hertz. Okay, so we have discussed the signal representation. So we will continue this signal representation further. Okay.